Hello, this is Dr. Keith Schubert, and as many people have asked for now for the Kalman filtering course, I am doing a brief intro to linear algebra, kind of as a reminder and refresher and whatnot. So it's not a full substitute for a linear algebra course, because in the next few minutes we're going to go from the very basics all the way up to singular value decomposition. So starting off, let's take a look just from addition as it goes in. Um, and remember, this one to me is very crucial. And I know this, almost sounds tedious, but when we get down to programming these, making sure you verify the sizes of things before they're added. This is one of the most common sources of errors inside the programs. So while this is often neglected in humanity as it goes, it's actually probably one of the bigger ones in programming. Remember that they will commute and associate. That is not as universal when you get to multiplication. You can't change the order. They don't commute. So you can regroup them, but you cannot commute them. Once you go to a floating point computer, association even really technically goes away, because order of operations will affect the error round-off. So you'll get a slightly different answer when you associate. So technically, by the time you get down to a programmed area in multiplication, you just pretty much have them where they are. Now, we do actually still commute them, but we commute them in the algorithm, and you got to think at that point, what is it going to do and which one's going to get me closest to the original? So when you deal with addition, it's pretty straightforward. It's just element-wise, by which we mean you take the first element A plus the element D, and there you go, B plus E, and that gives you the next element, so on and so forth. So the next step towards true or multiplication of matrices is an inner product. So inner products are really important to us for a lot of areas. Now it's one type of vector multiplication. That's bad spelling on my part. You notice I double hit that. Okay, so there's outer products. Outer products in vector areas are, so if this is an inner product, an outer product would be A, B transpose. So outer products make matrices. Cross products, inner product plus cross product are the two halves that make up quaternion multiplication, and this is what was split apart in physics when they went through them. So sometimes cross products are thought as that second one, although technically outer product is the reverse. But for quaternion multiplication, cross product is the one that comes from the imaginary portions, and inner product from the reals. Let's see, convolution. Convolution is used essentially a lot inside system theory as it goes in, and it's very similar actually to inner product as it goes. If you think, if you took inner product and you did it for functions, and here we're doing on the infinite domain, although you could do it from 0 to 1 or whatever, you'd just be multiplying the two functions and summing them up. That's inner product. When you deal with convolution, you're dealing with shifts of one of them against the other. So you're shifting and multiplying. So you would have in here, a tau minus t, something like that, where there's a shift that's going on. Correlation is the same thing, except you don't flip one of them. So whereas you would have positive t on one and you'd have tau minus t on the other, for correlation, both the main variables are coming in as a direct the same sign on them. For us, we're going to be dealing, with the sum of product versions. So just as a note, this angled bracket, this is the mathematical form of notation. That's pretty standard across the board from everything I've seen. So this is just A, inner product B, and it leaves it generic, so I could be doing it as matrix, transpose, and multiply. I could be doing it as integrating things, a lot of other forms depending on whatever area you're in. This just keeps it as a generic idea. In our particular case, it'll be transpose and multiply, and we multiply the corresponding elements. So you take the first to the second one, or first to first, and the second to the second, and the third to the third, and then you add them all up. So you get AD plus BE plus CF. That's, sum of products is another very common thing you'll find across engineering areas. So once we get to multiplication, we want to take this same idea now. If we're multiplying these two matrices, these ones are compatible because you've got, if you look at the columns of the first and the rows of the second, they have to be the same. And the reason is you're taking an inner product of this with this, and the second one with first, and so on, to generate the answer. So you need to have them have the same number of columns here as rows here, because they have to be compatible for that inner product. The final answer, you're going to have 3 different vectors here, 3 row vectors, and 2 column vectors, so you're going to end up with a 3 by 2 final answer. So that's the size of the result. And then the elements is just going to be the inner product, as I mentioned, corresponding rows and columns. So what I want to do is I put them into this form where I put the first one above and the second one to the side. Then what I've done is all these ones here in the green column are going to be composed of the first column vector of the second matrix, and all the ones on the yellow side are going to be only using this second column. And then I'm going to move this blue one down as we multiply them, so that hopefully this will let you kind of isolate each of the individual answers of them. So I've got E times A plus F times C. That gives me my first. It's the first row and the first column. And you just look to the left and above and you get the 2 elements you want. Here I look above and what I see is this, my yellow one and the blue one. And so I get E times B plus F times D. There we go. And then I can just keep marching down these columns, and you can see again I go GA plus HC. That gives me the here, because that's above me in the green area, and this, the blue, is to the left of me. Similarly here, above me is yellow and blue, so it's GB and HD. So you can walk through, and we do that for each one in terms of the final. Again, don't get confused. IJ is not, in this case, the imaginaries. They are indeed just letters for me. So I just did this generically so we could see them, and you can handle that last column, I think, pretty straightforward. So we can see from this one, now that we've multiplied them all out, that the product of this and this is just here as we have calculated. So hopefully multiplication is something everybody was very familiar with before, but it becomes important to us later on, so I want to make sure we were all on the same page. Now, we get into other areas. We want linearly independent vectors when we deal with things. And what does this mean to be linearly independent? Well, that means no non-trivial combination of them can be 0. So imagine I had 3 vectors, and this ABC, and this DEF, and this GHI. And alpha, beta, and gamma are 3 scalars that are going on. This dot is just the bullet for the PowerPoint. So that's kind of annoying. I should have removed it. Oh well. What we're saying is that I want to make sure that there's no alpha times ABC plus beta times DEF plus gamma that GHI that gives me all zeros. That's not what we often call trivial. So a trivial combination is 0, 0, 0. So if alpha, beta, gamma are all 0, then trivially this adds up to 0. So a non-trivial means they cannot all be 0. So for some area where they're not all 0, is there some combination alpha, beta, gamma that adds these up that I get to 0? If that's the case, they're linearly dependent. If it's not the case, then they're linearly independent. So that's the goal that's going on. So consider the following, right? I've got the vector 1, 1, 1, and I've got 0, 1, minus 1, and I've got 2, 3, 1. They all look very different and everything else. So the question is, are they linearly independent or linearly dependent? In other words, is there an alpha, beta, gamma that makes them add up to 0? So consider alpha equals 2, beta equals 1, gamma equals minus 1. So I'd have 2 times 1 plus 1 times 0 plus minus 1 times 2, and I would get 0. And then I would have 2 times 1 plus 1 times 1 plus minus, so I'm up to 3, plus minus 1 times 3, minus 3, I'm at 0. And then 2 times 1 plus 1 times minus 1, right, plus minus 1 times 1, I'm back to 0 again. So indeed, 2, 1, minus 1 actually causes all these to add up to 0, since there is a non-trivial set of alpha, beta, gamma, then these three vectors, right, 1, 1, 1, 0, 1, minus 1, and 2, 3, 1, must be dependent. If it didn't exist, then we would have independence, but it does, so they are dependent. Now, what we want to do then is extend this idea. Now we've seen we can kind of break vectors up into individual little components. That's what linear dependence and independence means. We can find the independents give you the smallest set that kind of cover an area. The span is a space that's defined by all those linear combinations. So again, we're getting back into linear combinations. And the span says, if you give me a set of vectors, here I've just done 2, but you could literally have, I don't care how many we want. You want 1,000,000? Great, 1,000,000. Whatever size you want. The span is every single thing that can be written as a linear combination of any of the vectors inside the span. So it's just all the combinations. And so the dimension of the space is going to be the number of linearly independent vectors. And that gives us a measure of the size that goes on to it, and that becomes very important to us because we're going to be heavily dealing with what size of space we are handling on. Now let's take a look at a particular space that we care about. So this is the column space. And the set of vectors we're going to consider are the columns of A. So if you consider your A matrix, and it's made up of column A colon 1 all the way down to A colon n, these are all the columns of A. We want to consider the span of all those columns. That means it's any vector that can be written as the sum from I equals 1 to n of a column times some little x sub I. Now, if you look at that, and you were to add these all up, you would get A times X. So this makes some kind of sense. Where did we originally get that A times X? Well, we got it because we're saying, is there some vector B that can be written as some combination here? So we're actually asking for what is the component breakdown inside the span of the column space. Now realize the span of this column space does not have to be the entire space in which this lives in. In general, if there are more rows than columns, it's not going to span the entire, let's say there's m rows and n columns. It's not going to span all of m space. If n is less than m, you're going to span an n-dimensional at most subspace inside there. And so that means if you were to pick a B at random, the likelihood of it being in that subspace is very, very small. It could be close though. And so what you're doing then is finding the closest vector in that subspace. And this becomes kind of crucial to that whole idea of a projection lemma and everything else. This is where it kind of boils down for us. So we need to start asking some questions about this to see what can we describe and how well can it go and get the best we can do. So now the range of A this is one of the things to say, right? We're taking a look at A. What's its range? What can we actually describe with it? This tells us what B's will fit within it. Well, the dimension of the range of A is the rank of the matrix. That's how we kind of define that. And the rank is the number of columns. If the rank is the number of columns, then it is a full column rank, right? Now, the idea of making this jump from the dimension immediately to the number of columns that goes on comes back from what we had put a sec ago on the span area, that the dimension is the number of linearly independent vectors. Well, what we're asking here when we come back to the column space is, since the rank is that how many of them there are, this is now the number of columns. If the number of columns is n, that means rank equals n. We call that full column rank. If you're into math, this means it's one-to-one or an injection. Injection if you happen to like French mathematicians of the early 1900s. Bourbaki, the famous French math group that claimed to be a person, entered that name. But what that's telling you when you're going on here is, that you've got a one-to-one correspondence between the elements that you're mapping to, and that's important with to have the column rank to be equal to the number of columns. And so that removes the null space from A, and that's a very nice feature. Because it is one-to-one, there is no null space to A. Now, that doesn't mean there's no null space to A transpose. There's just no null space to A, so there's no right null space. To get the other side, since I've introduced the idea of right and left null space, to get to the other one we have to look at the row space. The row space is completely analogous, right? So you take A transpose, and now you break it into columns. So the second I've transposed it, the rows have now become columns. So when I take a look at breaking it up into columns, then I can take the span of those, but this is the rows of the original matrix. I can now write vectors in terms of these. And so therefore the dimension of the range of A transpose is going to be the same exact rank R, it's the same matrix. Right? If the number of independent rows happens to be the number of rows, then we have a full row rank matrix. This is what's referred to as onto or a surjection that's going on. If you're both one-to-one and onto, or if you prefer the terms injection and surjection, then you become what's called a bijection, and that's when matrices are invertible. If it's onto or a surjection, there is no null space to A transpose. I say no null space, that's kind of a bad way of saying it in some sense. You always have zero in the null space, but essentially you have no non-trivial things in there. You don't have any vector that'll build the space of dimension 1. So the dimension of the space is less than 1. So if we consider these now lead to, we've now introduced 4 fundamental spaces. If you understand it, we've got the column space, and we have the null space of A, and we have the row space, and we have the null space of A transpose. That leads us to what's called the 4 fundamental, often this is called subspaces. I like to just call them spaces, but I mean technically I guess you could call them subspaces. But I think they're awesome enough in my mind to do it. There's a couple ways to draw these. Sometimes people make them, kind of different size. Like one's a rectangle, one's a square. That doesn't make me think anymore that these are hyperspaces. What you got to understand is these are hyperspaces. We usually draw these as right angles so that you understand these are orthogonal to each other. So we really do mean this entire space is orthogonal to this space. Similarly here to here. But they're not just dimension 2. They're whatever dimension they are. So this one is rank R, so it's dimension R, and there are n columns, so here this is n minus R, what's left over. So that's why if this is r becomes n, then this one's dimension becomes n minus n, or 0. So it becomes dimension 0, so it only contains the point 0, which you can think of as the intersection there. This is the null space of A. This is the row space of A that's going on. So this is the span of the rows of A, or the range of A transpose. This is where X lives. So X is made up of a bunch of rows. So if you think of AX equals B, X is multiplying each vector in the row. It's an inner product to find out how much is it weighting in each direction of the different potential vectors that span this row space. When you're doing that, you're multiplying, and that ends up giving you all these little weights. Well, all those little weights are also can be thought of as, you can take the individual xi's, x1, x2, x3, as you build x up, and x1 is multiplying the first column, x2 the second column, so on and so forth. So another way of thinking where those weights live is those weights must live in the column space, because it's just a series of adding up the columns. So A maps you from the row space to the column space. So X lives in the row space, and your best guess at B lives in the column space. That's the span of the columns, or the range of A. So if A takes you over, A transpose has to take you back. Right? And that means that this must be the null space of A transpose. Again, this is the same rank R this was. So both of these are dimension R. And this is therefore M minus R, because there's M minus R rows. And that's why if R equals M, then M minus M is 0, and the null space goes away. So that's that earlier observation. A will map this null space over to 0, and A transpose maps this null space to 0. Now, if this null space and this null space, both A and A transpose's null spaces, are 0, then all you have is going back between these. They must be full size, and you can always go from here to there and back again. Well, that must be invertible, so that's when you have an invertible matrix. This one completely describes everything we want to know about linear operations, and as a result, this describes what the basis of our singular value decomposition is. So if you think about this one, what's going on in a singular value decomposition? Let me start actually at the middle here, the singular values. These are the non-zero singular values, and let's assume there are some 0 ones. It's possible. We've grouped them all together here, and then we've got the off-diagonal terms. V1 multiplies sigma, V2 multiplies 0. So, this one is, there's R of them. So this is the first R of them, and this is the remaining N minus R of them, because it's got to be equal to the columns. Similarly here, this is M, because it has to be equal to the rows off this, and so this is R, and this is the remaining M minus R. So if you consider that one, this is multiplying into X, this is finding out which of the basis vectors. So this is a basis vector for these spaces over here. And V1 spans this particular range space, and V2 spans the null space. And then U1 on this side, it's mapped to sigma 1, that spans this range space, and U2, oops, I did not type that correctly, that's definitely a changer. I hit the right key, and that's U2, and that spans this one. Oops. So no matter how many times you check these, and I check these for a couple days here, it turns out you always notice this one down here should be the span of V2. So let me see if I can. I'm gonna have to fix that later as it goes. But we've got V2 down here. So this is V1 transpose span, this one's V2 transpose span, this one is U1 span, this one's U2 span. So we actually, if you think about the singular value decomposition, is just giving me these ones the definitions of those four fundamental spaces. First are columns, first are rows, remaining, and the remaining. Now, in addition to this, these ones here, if you look at the dimensions, so these are the dimensions kind of placed into the vectors as they go. If you just consider these are here, the zeros are fairly trivial. That's describing these arrows. So these zeros here describe the mappings that are going to the zero area. But these sigmas are telling us, the first ones are, say take the ith one. It's saying I'm taking from basis vector vi over here, and it's being mapped to ui while being weighted by sigma I. So it's a direct mapping that goes on with a weighting. When I'm going backwards, it's just taking ui to vi transpose with a weight 1 over sigma I. So the actual mapping arrows that are going on is related directly here. That's why the inverse, you just go straight forward, or sorry, the matrix you go straight forward. The inverse, when you're coming back, you just do 1 over. So in truth, you can just get a weighting of 1 if you're going around the loop and you're directly on one of those vectors. Well, then we just decompose them into those vectors. What are your components in each one, and we can now nicely handle it. This is why singular value decomposition does such a good job when it's handling the inverse, because it will nicely weight them forward and back. The only time you ever run into problems is if there's errors that don't come across on one and come back on the other, say due to numerical precision inside the machine or something. Some tiny amount comes off and then comes back the other way. If there's a huge weighting difference between the two, you can get scaling issues that come off on those. But in the straightforward math, what should happen, this is where it goes. It turns out that is very small and rare, so you tend not to get those type of errors with SVD, which is one of the reasons why people use it, even though it's kind of large and complex. There is a lightweight one, which doesn't do the null spaces, that you only get U1, sigma, and V1. They're the only non-zero calculations, so we often call that the lightweight singular value decomposition. Technically, that means these are not fully invertible as the proof goes in, but you can solve it assuming you have the whole thing, and then the solution will only involve U1 sigma and V1 transpose, so then you can actually, when you implement it, just do the lightweight one, and the lightweight one is much faster. So that gives you some improvements around. So that's kind of my whirlwind tour from how to add to singular value decomposition. Hope it helps, and I will see you in class.